Yeah, so thanks for inviting me to the ESAO series. I will talk today about concepts, concept combinations, and the truth operator. And just like Maria's talk, this is completely over-ambitious for a 30 minutes talk. But um, hopefully we get to see the big picture. So Maria helped me a little bit phrasing, giving some background about a series of concepts, which we will see in a moment. First, before I start, I want to point out the logic part that I will talk about is based on joint work with a large number of people, which you see here at the bottom of the slide, especially the early work on tooth operators with Claudio Massolo and Daniele Porello, and later a lot of technical work also with Pietro Galliani, Gwendolina Righetti, Nicolas Trocois, and then Gabriele Sacco, Loris Bosato, Roberto Confalonieri, and Maria Hedblom, who just spoke before me, worked on a number of applications of this stuff in the area of conceptual blending, explainability, and so on. So what is this about? Let me try to give you a kind of a high-level pitch for what kind of problems we try to address, both with the logic and with these the general space of concept and concept combination. And also to address the educational part of the ESAO series, we talk a bit about Tarski and Quine. So since we're here in an ontology space, logic is very important for us. And when we think about concepts and dealing with concepts and formalizing concept, we do this typically with logic, and we are deeply drowned basically in this classic paradigm, which comes from Tarski, of course, which is the recursive definition of how we evaluate sentences, and which Quine, following Quine, is the disquotationalism, which we often teach our students with the line "snow is white" is true if and only if snow is white. And if we bring this down to a simpler case, we talk about John being a cat. How do we evaluate this? We consider cat some predicate, which we interpret with the help of set theory. We take John as being an individual, and the membership of John being a cat is evaluated as membership of the element that John denotes to the set that the predicate cat denotes. So far, so good. And this brings us to classic Boolean logic and first order logic. In the bottom right of this slide here, you see a little illustration how, let's say, children think about cats and dogs. And if you ask them to come up with what do they have in common or give me a cat dog, they will say, yeah, it's some beast that has still 4 legs, and it has fur, and it runs and it jumps and so on. You might drop certain properties from this idea. Maybe that you think dogs don't like yawns, so you take this out. So the combination of the cat dog creature pet, it will neither be a cat nor a dog. Okay, so just to ground the problem, there's a big gap between this kind of conceptualization and what we do in logic. We talked a little bit about AI, current AI, generative AI, just as a preview. The idea to combine concepts in ways where there's no natural fit to build a conjunction can end up in things like a fish vehicle. To the right on this slide, you see a beautiful fish vehicle flying over the ocean, which any generative AI has no problem producing if you give the tool the words to trigger the image production using a lot of bias, what birds and fish and vehicles look like, and putting together some features, filling in detail. On the left, you see the result of a, let's call it cutting edge symbolic system that takes descriptions of concepts, puts them together into a nice symbolic description of a fish vehicle. It's nice if and only if you read the axioms and the descriptions of this concept, they make sense. And if you take this description, give it to an AI, it will produce this monster that you see on the left. So what you see here is that although these systems are, have very high performance, again, there's a big gap between the symbolic description and representation of these concepts, what these AIs do, and what we have in mind when we talk about these concepts. So the way this comes out here on the left is by not calling this a fish vehicle, because then it will be immediately biased to the image that you see on the right. You call it the X such that, and then you describe it, its properties, which you can sort of, you find these X are related to, birds and so on. I don't know. This is sort of a preview, what comes out partly of the research we're trying to do. Now, let me go quickly through a few examples regarding concepts. So I want to talk a little bit about concepts to get to some distinctions regarding this space of the attitudes you can have towards concepts, then about combining concepts, and then about all more recent logical approaches to dealing with a specific corner of prototype theory. So here's a chair. The examples I have here, the definitions are taken from Wikipedia, and I just show a few of them to make some very coarse, obvious distinctions in this concept space. So a chair is designed for one person, consisting of one or more legs, flat angle seat, backrest, it may be made of certain materials, and so on. What's important about it? Without the human agent, there is no chairs. There's things that you can sit on, but there's no chairs. Chairs are a human category. If you go to prime numbers, again, it's a very familiar concept that we all know, but it is not dependent on the human. It is arguably not dependent on being observed. Philosophers consider it sometimes to be a Platonic object. There's a sequence of these numbers. You will not understand this concept by seeing one prime number after the other. So it's not what we call, learning exemplars. There's also no great similarity between these numbers. You have to understand what makes a prime number a prime number. You have to understand the definition. This is a maybe good example for what is called the theory of concepts. You give it precise definition of what falls under a concept. Examples from physics. So friction, again, is a very familiar concept. It's quite easy for AI systems to recognize, qualities of materials, to detect friction and so on. For humans, it's a quite abstract, difficult to grasp concept, and its definition involves essentially advanced physics and mathematics. Species. So we know cows. We have a vague idea of the notion of a species, but if we go again to the Wikipedia article, we will learn that species is a very hard to define notion, and it's a meta concept and something that we struggle to really define in detail. However, cows are easy to recognize. Indeed, we can put up a lot of cows. We see a lot of similarity between these cows. We can see they all have a nice cow posture here. And this is an example where you immediately recognize you could figure out what cows are by seeing lots of cows, observing the similarity and sharing certain features between these animals. So what Maria talked in the previous talk, she explained to us the connection between affordances and image schemas. And so I will just build on this introduction already. If we think about the chair, and you see a lot of examples here of chairs, it's quite obvious that this concept is not based on similarity. I can show you a number of chairs that all look completely different. To figure out that there's certain uniformity to this concept, you need to figure out that what makes the chair a chair, the chairness, is providing support to the agent that wants to sit on it. And typically there's verticality in it. You don't sit upside down unless perhaps you are in outer space, right? So you can stretch this concept of chair but the support is the most essential one. So what these examples show us that the space of talking about concepts is quite complex. Certain kinds of concepts fall neatly in one of the approaches you see on this slide. So exemplar theory is the idea that you learn a concept from seeing many examples and figuring out the criteria to include and exclude certain entities. The knowledge theory gives a theory of a concept, such as for the prime numbers. We have the geometrical view, which essentially is Peter Gerdenforsch conceptual spaces, so where you have certain features that give you a geometric quality space in which you carve out convex regions, such as in the color spindle, to define certain kinds of colors. The prototype view that I will talk a lot more about later. And then theories that acknowledge the messiness of the whole idea of concept, namely that you can just reject the idea that there is such a thing as concepts, or you make some kind of, like Antonio Lieto proposes, proxy type theory, where you have a structured approach to figuring out which is the appropriate theory for a particular class of concepts. So this describes vaguely the landscape of concepts. Now, I only talked about individual concepts. In my opening remarks, I talked about the fish vehicle and the cat dog and so on. So what happens if we try to put together concepts? And we don't have really much time to go into great depths about this landscape either. But so I want to point out that, first of all, there's a quite strong cut between language-based combination approaches and issues and really cognition and psychology-based approaches. The theory about conceptual blending, which is about mostly issues of creativity and how you can discover new concepts by blending selectively known concepts in the bottom right corner on the slide. Mostly pushed by Mark Turner and Fauconnier and so on. This is really about the concepts being represented as mental spaces and being blended mentally and then realized later and maybe described also as symbolic artifacts. So I will not say much more about this. Today I want to talk about some of the other issues that you see represented in the other pictures, such as overextension, head and modifier distinction, and underextension. Let's have a brief look at these. So James Hampton did a number of experiments in the 1980s mostly to study how people build conjunctions. And this is interesting for us. So this is driven through language, how you express these conjunctions, and so linguistically and reflecting the psychology of how humans make sense of the conjunctive concept. And there's a number of effects that I want to mention here because they immediately break what we had at the start of the talk. They break Boolean logic. Okay, so if I have conjunction of two Boolean concepts, cats and dogs, either the intersection is empty because they don't share certain properties, or it's not empty, and then what's inside this intersection is both a cat and a dog, a specific one maybe. So in the head and modifier combination, which is some kind of conjunction, it's not commutative. So a poet-painter is different from a painter-poet. So if you want to describe this with logic, you have to have a non-commutative sequential definition of conjunction. And I think most people, this is why it's been studied by psychologists, most people agree, there's empirical evidence about what people feel about these kinds of conjunctions, and they admit certain examples and counterexamples in the way that I show you here. So an overextension is a conjunction where there's more in the conjunction. So I do something like A and B, A's that are also B's, and there's more in the conjunction than is in the set theoretic intersection. So you can say wrestling is a sport, and you say wrestling is not a game. You disagree that wrestling is a game, But you might agree that wrestling is a sport that is a game. Okay, so the operation of conjunction is something else than the intersection. And the dominance is something similar where one concept dominates the other one in the conjunction. Okay, so this is the motivation for some of the motivation why we study non-classical logics in general to try to model some of these effects, both in the representation of individual concepts, but also in the combination process, such as building conjunctions, building impossible conjunctions, doing conceptual blending. And it's clear that this cannot be just done by writing down first order logic formulas and applying task in semantics. We have to do a little bit more. So just one attractive corner to think about alternative formalizations is the prototype theory corner. And so I mentioned this before. So one of the first papers that formalized this with logic was Claudio Massolo and Daniele Porello. It was at FOIS, using first order logic to formalize some of the prototype theory in logical terms. And what you do normally is that you have here in the slide, you have the fish, you have certain kinds of features that are important for people. They're important in different kinds of degrees. And if you have enough of these features, you accumulate the features, you have some kind of function that accumulates the weights of these features. It can be also a complex function, meaning more complex than just adding up the numbers. And then there's the idea of, just like in machine learning, in perceptrons, thus the name, you accumulate enough of these weights and then some threshold will be reached where you confirm your affirmative about concept membership. Okay, so this is roughly the idea in general of prototype theory and the basis of the perceptron logics, also known as truth logics, that we are studying. So just a couple more words about prototypes. So to understand what's going on in this corner. So there's always, even if you talk about features and their values, their weights, there's always a notion of similarity hidden inside, because if you have a lot of features, you're typically considered a better exemplar, a better example, perhaps, or at least you can define, you can place all the objects into a space and see where there's more examples of that kind. So what we see here in the example is that if you have some apples and they have certain features, it's not the case that if you add up all these things, you get a better apple. Okay, so the apple that has all the colors is not a better apple than these three perfect ones that we have on the left. And this is normally not immediate in the description of the prototype concept, but depends also on additional knowledge, background knowledge that we might carry with us. So why is this interesting in general? Because you can use it for a lot of KR representation issues, problems, and also in the more creative corner. So you can use it to accept the dog that had an accident and only has 3 legs, which will not satisfy the canonical definition of a dog because it's a 4-legged animal. But it still has a lot of the dog features, so we will easily be happy to accept this dog as a dog. But logically, it's difficult to allow these kinds of exceptions in logical frameworks. In the lower part of the slide here, you see the ideas of combining concepts, which can either stem from the conceptual blending framework or just from sort of creative concept combination following different paradigms. Okay, so let's get to the logic part of the talk. So I'm leaving out some of the more complex questions in this framework. I want to convey mostly the basic approach here. And let's first look at this majority operator. So what is the majority operator? And here you also see, maybe for the first time, if you look at this symbol here, you can recognize the twos, right? So this is why this logic, you know, this operator is called the twos operator because it looks like a twos. So what goes in here is C1, C2, C3. If you know description logic, think of them as concepts, but they could be also propositions, okay? If it is true, C1, I give it the value 1/2. If C2 is true, I give it the value 1/2. If C3 is true, I give it the value 1/2. What is the majority concept is all the things that satisfy at least 2 out of 3, so the majority of the concepts that I list here. If you think about it combinatorially, especially if there's a lot of choices, if you put 10 concepts there, the majority, let's say, would be 6 out of 10. There's a lot of combinations that you need to figure out and verify to see if something is in the majority concept. If you have any doubt that this is somehow interesting or great, let's have a quick look what Donald Knuth said about it. At the top of the slide, the majority operation is probably the most important ternary operation in the entire universe because it has amazing properties that are continually being discovered and rediscovered. Okay, so this is from one of the last volumes of Knuth's The Art of Computer Programming. And why is he saying this? Because it has this feature of really compressing the combinatorics of satisfying subsets of these concepts. Okay, so how do we? So the major shift that we made here is from the idea to just look at features and giving them weights to turn this into a concept forming operator. Okay, so this was the major move, trivial on some level, but powerful move in the same way that you introduce the for all quantifier into first order logic. The for all quantifier is an infinite conjunction, right? If I say for all x, I'm making a conjunction over every single object in my domain. If I introduce the twos operator, I'm allowed to directly form in a compressed way these expressions that put a threshold there and look at the combinatorics, how I can reach this threshold. Okay. So it should be quite obvious that this has a direct connection to circuit theory because what it does essentially, it gives a linear representation of the basic mechanics of what a perceptron does, also in neural networks. And before I summarize a little bit about the results, what comes out of this, let's briefly reflect what we can do with this and also connecting to some of the questions from the last talk about neurosymbolic reasoning. How can you make this work in different setups? So here's a bunch of cats. We know how to train a machine learning classifier to recognize these cats. They might use obscure features that we don't understand. If we look at the pet concept, it will be more obscure features because it's much less obvious similarity between these creatures, but still somehow you can also learn pet concepts with a bunch of features. Now, how do we use this and intend to use this together with this twos operator? You can imagine you have these cats just in the same way that you train machine learning classifiers. If you have a bunch of cats that you know how to recognize, you can import this concept, as you see here in the bottom left corner. You can pick these features, h1 ... hk, figure out the weights of these features, and you know when to fire because that's what you've already learned. And you take this description and you can just write this into your knowledge base. Okay, so basically these variables make the interface to a learning tool. And this is one direction in which you can do this. And also these features are itself concepts, the ones that are inside the tools, so they can be learned. And you can have a deep neural network by nesting these tools operators. And if you go higher in the abstraction, at some point, these can be tweaked so that we can understand them. And at some lower level, you stop caring about the features, you just maybe accept that we figure out whether they're true or false of a certain object. Okay, so that is the big story of how this works. So how is it implemented? We start with a standard description logic. So I don't have time to go through this in greater detail. Should just remind you what this looks like. So it's essentially fragments of first-order logic with a concept-based language. Concepts denote sets, and then you have concept-forming operators that allow you to build more complex concepts. And the basic tools logic simply takes some description logic, so here it's ALC, and it adds this tools operator as another concept forming operation. So you have here C1 up to CM, you have some weights, and this expression is a new concept, just like all the other concepts. So you can apply the other operations to it. You can nest this. You are completely free to use this as any other DL operation. And the semantics, which I already explained informally, is that some object belongs to these tools if and only if I take the D, I check for each concept whether the lowercase d belongs to C. If yes, then I take the weight of the concept Ci. If no, I don't take it. Okay, then I accumulate these weights. If I reach T, I belong to the tools. If I don't reach T, I do not belong to it. So a quick example how you can use this. This is the Florida Criminal Punishment Code. It's not a happy example, but it's an educational example. Okay? It's a real document where for each crime you get certain points. And if you reach a certain threshold, it's the concept of compulsory imprisonment. And if you look more closely, you realize something that is a bit more complicated, namely, and that is true in most countries, I guess, if you commit a crime several times, you get charged for every count of that crime. Okay, so you steal one time, you get 1 point. You steal another time, you get 2 points. Maybe even consecutive crimes might be more costly and so on. So without going into details here, counting, giving weight to the counts of committing the crime is not expressible in this basic tools logic. You need for this tools operator that can count, namely where you count each time you commit a crime, you give a certain weight. Okay, so this is it's already an extension of this paradigm which we studied, which still is inside the DL framework, which still is decidable and has very nice properties. Okay, so the first core result about this was from 2020 paper at the ESAO conference, where we showed the basic tools logic can be encoded back into standard description logic without exponential blow-up, which essentially means that this setup for using it in learning environments in the standard tool ecosystem is feasible. If you push this further, then you might still be decidable, but it's not in the standard ecosystem of standard DLs anymore because it's not expressible in these standard DLs. So to give you an idea why this is in the standard DL framework, you can just look at what do these tiny tiny t's do. Okay, so all the standard Boolean functions that you see illustrated here, they're just these short two's expressions. And maybe to put out something, point out something more interesting here, if you have, or let's look at a conjunction here. It's not C1 and C2, right? So you're doing a conjunction, but you need to reject one of the concepts. So to reach the threshold 1, I need to be a C2, but if I'm also a C1, then I will add up 1 and minus 1. I will be 0. I will not reach the threshold. To reach the 1, I need to be a 1 and not be a C1, okay, so that I remain at the threshold. So you need this minus 1. You need these negative numbers. If you drop it, there's a direct relationship between being able to express negations and having negative numbers, or punishment for concept membership, essentially. Okay, so you can show that you can know the standard Booleans here. And also, since really the analogy to perceptron and Boolean circuits is very close, so we know that XOR cannot be built in a Boolean gate, in a shallow Boolean gate, right? You need a nesting of these operators. And the technical explanation for this is that that they are not linearly separable in this space of evaluations. So you see the exact same phenomenon also in this tooth operator representation. You cannot say XOR with a flat tooth. Unless, as we do here in the second line, you allow complex concepts in the flat tooth. If you want primitive concepts, you need to go deeper and you need to nest these t's, and you need for the negations, the negative numbers, and so on. Okay, so this is unavoidable and mimics the behavior of Boolean circuits. Okay, so we studied this formalism also from the understandability perspective. So if people look at this formalism, can they deal with it? Is it bizarre and crazy syntax, or is it nice and easy to understand syntax? And people can deal with it quite well. I mean, you just have to add up numbers. Obviously, if you have these very big expressions and nestings and so on, people will fail in the same way that they would fail with huge Boolean expressions. But in the examples that we studied here, they were comparable, and people without formal training in logic were actually doing better with the tools than with disjunctive normal forms. If you want to apply this to more complex situations, such as the exceptions that I mentioned before, modeling the dog that has only 3 legs and so on, often you want to study situations where you can prove from your knowledge base that John is a cat, John is fluffy, and so on, right? You want to prove that features hold and not just evaluate in some model whether this is the case. Okay, so this is the difference between provably true features and accidentally true features. And it's important, of course, if you want to distinguish also between necessary and contingent features of concepts, so such as the chair, it needs the containment, otherwise it cannot be a chair. Sorry, not the containment, the support. Chair without support is not a chair. So you would want that chair, the support property cannot be taken out. It's a necessary property. If you formalize this in a naive way, you run into paradoxical situations. So we call this the Rudolph paradox, because Sebastian Rudolph was pointing out to when he reviewed Gwendolina's PhD thesis. He figured out, just like Bertrand Russell did, that our system, the naive presentation, is giving you an inconsistent entailment relationship, because you can define concepts that rely on negating themselves, and then you run into serious problems, and you need to stratify this language by distinguish between features of different levels of abstraction, essentially, just like in set theory when you build up features and concepts over hierarchies. And we've done exactly this in a controlled way in the work of Gabriele Sacco, where he built a non-monotonic logic based on prototype theory and tooth operators with something like this knowledge-dependent concepts. Okay, so just to wrap up this story, we studied various extensions of these tools. What you see on the slide, I'm not talking through it, and I've not even shown you the full extension with the counting perceptron, but just to point out that if you use this formalism to a certain level, you still can encode it back into standard DLs, which is a very useful feature for using this in practice, hooking it up with learning net frameworks and using this in a sort of neurosymbolic setup. If you do expressive counting, some interesting things happen because you really have very expressive logics. They're still decidable, but they extend all the ways that standard DLs can count, but in a good way. But you don't have this natural reasoning support anymore. And the succinctness results show that some of these logics really are strictly more succinct than their DL counterparts. Okay, so I can end here and just show you this rather long list of directions for future study, because there's really a lot to do here, both in terms of understanding applications and how they connect to. So, thank you.